Forget everything Star Wars taught you about faster-than-light travel. In science fiction, ships jump to light speed and cross galaxies in hours. In reality, even traveling at the speed of light wouldn't solve our interstellar problem. The Milky Way is about 100,000 light-years across. That means even at light speed, the absolute cosmic speed limit, crossing it would take 100,000 years. And here's the brutal truth of relativity. The closer you get to light speed, the more energy you need. As you approach it, the energy requirement approaches infinity. In other words, accelerating a massive object to light speed is physically impossible with known physics. So how do physicists even talk about warp drive? In 1994, physicist Miguel Alcubierre proposed a loophole. Instead of moving a spaceship through space faster than light, what if you moved space itself? The Alcubierre drive suggests contracting spacetime in front of a spacecraft and expanding it behind. The ship itself would remain stationary inside a warp bubble. From the outside, however, the bubble could move faster than light relative to distant observers. It doesn't break Einstein's laws locally. It bends spacetime. Sounds elegant, there's just one problem: exotic matter. The equations require something called negative energy density, a form of matter with properties we've never observed in usable quantities. Some quantum effects, like the Casimir effect, hint that tiny amounts of negative energy might exist. But scaling that to power a warp bubble is another story entirely. Early calculations suggested you'd need more energy than exists in the observable universe just to move a small spacecraft. Later refinements reduced the requirement, but we're still talking about astronomical, almost unimaginable energy levels. And that's not the only issue. There's the causality paradox. If you can effectively travel faster than light, you open the door to arriving somewhere before you left. Then there's the bow shock problem. As a warp bubble travels, it may accumulate radiation and particles at its front edge. When the bubble collapses at its destination, that energy could be released catastrophically. Steering is another challenge. Some models suggest you can't control a warp bubble once it forms. You'd need to set your destination before launch. So where does that leave us? Warp drive remains a mathematical possibility within general relativity, but not a practical engineering project. In the meantime, more realistic concepts exist: fusion propulsion, antimatter drives, and even generational ships. Spacecraft where multiple generations live and die en route may be slow, but they obey known physics. And yet, studying warp drive isn't pointless. Even if we never build one, exploring these ideas pushes the boundaries of physics. It forces us to examine space-time, quantum fields, and the fundamental structure of the universe. So could warp drive really break the light barrier? Mathematically, perhaps. Practically, not anytime soon. But the pursuit of that dream might still lead us to discoveries just as revolutionary. The stars aren't moving closer, but our understanding of the universe just might. Like the video and subscribe to the channel.